Please welcome the CEO and founder of insitro, Daphne Koller.
Good morning, everyone. For those of you who know me as a machine learning person, many of you don't realize that throughout most of my career, I've actually been working at the boundary of two disciplines, machine learning and biology. And I say boundary judiciously because while I wish to have worked in the intersection, there really wasn't that much of an intersection to be had between those two disciplines. What I hope to do today is to convince you that that time has come, that we can really do work at the intersection of these two important areas. So I'm going to start by doing a very brief review of machine learning. I'm sure this audience is very familiar with the concepts, but it helps set up some of the concepts that I'll discuss later. So in the last 10 years, machine learning has made incredible progress, much more than I would have expected at the beginning of that period. I could give this example across a range of different areas. I'm going to use computer vision because it helps set up a lot of what I'll talk about later. Not that long ago, around 2005, if you'd shown this image to a computer and asked it the simple binary classification question, is there a bear in this image? It would have gotten it right about a little better than random. 2012, we already had more data. This was the era of ImageNet, where for several thousand categories, we had maybe a few dozen or a couple hundred images each. And so we could now do the multi-class classification, and we could show the computer this image and ask it what's in it, and it would probably have said wolf. Now, there's no wolf in this image, but it's a kind of wolfy-looking bear. So you could say the computer at least is partially in the right direction. 2 short years after, the label of this image from the state-of-the-art algorithm at the time is a brown bear is swimming in the water. The bear isn't in the water, but there's a bear and there's water, so it's pretty darn close. And then in 2017, 2 brown bears sitting on top of rocks. Today, in 2019, computers are able to label images with full-blown text captions at performance that is beyond human level. And they're able to do this for a problem that humans are really good at, which is labeling natural images with natural language. This is what we do most of our day. So what has enabled this ridiculous amount of progress? Of course, it's better machine learning models. That's obvious. But it rests on 2 important components. One is a very large amount of data. The images, the algorithm was labeled on 10 million images, and of course, the compute power of Amazon Cloud and others that allow machine learning models to be trained. So when you compare the performance of the new machine learning models to the old ones rested on a lot of prior knowledge from a human being. A human had to tell the computer that it needed to look at edges and little circles that resemble the nose of the bear and so on and so forth. And so because there was so much prior knowledge built in, they worked well even in this scarce data regime, whereas the more sophisticated algorithms that we use today didn't have a lot to rely on, so they didn't work so well. But the simple models asymptote at a modest level of performance, where now that we have more data, the new models are getting better and better all the time. And specifically, the way these algorithms work is they are given raw features without relying on human knowledge to tell it what to look for. And they're building new and better hierarchies of features upon features that in the end are allowing them to make very subtle distinctions between categories that even people have challenges with. So one important aspect of this is that the computers are actually learning a representation of the underlying domain and capturing hidden substructure. So if you think about the space of all images, say 1,000 by 1,000 even grayscale images, they sit in a million-dimensional space. Most of that space is white noise, not images that we would recognize. The space of actual images sits on a lower dimensional manifold. The structure of that lower dimensional manifold, if trained appropriately with the right objective function, captures important semantic significance. So for instance, if we put 2 images of trucks on this manifold, even though from an appearance perspective they have different color, different pose, different backgrounds, because the algorithm is forced to label them with the same label, they are placed next to each other in the manifold, thereby revealing latent semantic structure. Images of trucks or cars or tractors would be adjacent to this in the manifold, whereas cats and dogs and turtles would be somewhere else. This structure is something that you can interpret if you're a person in contexts where we understand the domain. But as I'll talk about when we get to biomedicine, when it's areas that we as people are striving to gain understanding, having the computer be able to reveal that on its own is really important. And sometimes the semantic structure is actually really interesting and profound in extracting the underlying levels while removing the surface. So here, for example, is an algorithm that was trained on images of winter and summer scenes, not the same scene in two different weathers, different scenes, and is able to extract the skeleton of the scene from the overlay of what makes good or bad weather, so that when provided an image such as the one on the top left and asked what that image would look like in a summer day, it not only removes the snow, it also changes the color of the sky, puts leaves on the trees, because it's understood how to separate these two semantic layers. Okay, so that was a very brief recap of machine learning, and I'm going to move to biomedicine, and specifically how I believe machine learning can transform this important space. Now, in the space of diagnostics within biomedicine, there's already been some reasonable progress. A long time ago, back when I was still at Stanford, I actually worked on machine learning applied to digital pathology, where the computer is provided images of cancer tumor samples under the microscope, the same samples that a pathologist looks at all day long. So this is what it looks like. And even back then, using old-style machine learning, the computer was able to make prognostic predictions better than your average pathologist. So we see at the bottom there is what's called the Kaplan-Meier survival curve, stratified by low-risk versus high-risk patients, where the low risk is at the top, the high risk is at the bottom, and this is how many patients survive for a certain amount of time. The x-axis is time. So this was considered better than pathologist performance back in 2011. Fast forward to 2018, a lot of people are now applying deep learning techniques to this type of approach. And what you see here is that not only is the performance now better than an average pathologist, it's better than an expert pathologist. So on the left, you see the stratification in the Kaplan-Meier curve between low risk and high risk of what is the best state-of-the-art human pathologist. And on the right, you see the stratification of the machine learning algorithm, and you see that it's performing better. But what I think is actually even more interesting is that the computers are now able to do things that people are unable to do because they are looking at data that people really find challenging. So this is a computer looking at those images and being able to tell not only what kind of cancer it is, but what is the specific genetic lesion that caused the cancer, what's called the driver mutation. And it's something that no pathologist is currently able to do. So I think that's a really exciting piece of progress, but it's also important to highlight some challenges that arise specifically when dealing with biological data sets, and that's the incredible variability and extent of confounders that one sees in these areas. So here's one paper that highlights this from a very recent paper. This is, again, a diagnostic task, learning to diagnose fractures from images such as the one on the left, and you can see that the deep learning algorithm does a pretty good job. I mean, you look at these ROC curves, you say, I'm doing well. But if you dig down and try and see what it is that the computer is actually learning, visualizing that manifold, you see in the graph on the top left that there's not a real stratification between the yes fracture and the no fracture, the blue dots and the gray dots. Conversely, the algorithm is doing an amazing job at figuring out what scanner actually did the scan. Now, it turns out that some hospitals treat higher-risk patients, and they use one kind of scanner, and other hospitals treat lower-risk patients, and they use a different kind of scanner. So the computer, by detecting which scanner did the scan, is doing a really good job at figuring out what's fracture and what's not. And when you correct for that, the performance kind of goes down to something that is only slightly better than random. So batch effects and artifacts in biological data are really important to keep track of, and also mean that we have to be really thoughtful about how we collect and how we generate data. Okay, so with that, I'm going to switch to what we're actually doing, which is therapeutics. Therapeutics, in some ways, has made an incredible amount of progress in the last 50 years, starting from vaccines, biological therapeutics, antibodies that are used both in cancer care as well as in autoimmunity, immunotherapy, cystic fibrosis, which is one of the true tour de forces of understanding the human genome, because it's by understanding specific genetic variants in the genes of individual cystic fibrosis patients that we're now able to give 90% of cystic fibrosis patients a chance at a normal life in what was previously a death sentence, and so on. So that's the good news. The bad news is what's called Irum's law. Irum's law is an interesting thing for those of us who grew up riding the tidal wave of Moore's law, because Irum's law, if you look at it, is a graph where the y-axis on a log scale is the number of drugs discovered per $1 billion of US dollar spending. This is on a log scale. So this is an exponential decrease in productivity in drug discovery for the last 50 years or so. Why is that? Why is it that a drug that used to cost $100 million or so to create now costs over $2.5 billion. It's not because the cost of that one drug is now 25 times higher. It's because our ability to figure out what it is that is going to make for a good drug is no longer as powerful as it used to be. So you start out with tens of thousands of different hypotheses, and as they go down into preclinical development and then clinical trials, by the time you have that one successful compound, it's carrying on its back the cost of tens of thousands of failures. Now, if you think about that, it's really a problem of prediction. If we could predict up front, even with modest accuracy, what's likely to succeed and what's not, a successful drug might not carry the same cost on its back going forward. So how do we solve this? How do we use machine learning, which after all has gotten really good at prediction, to address this problem? The key is data, and not just data, good data. So where do we find data that can help us deal with the problem of making predictions about what drug is going to succeed? Most drugs fail because they're targeting a gene that doesn't affect in the right way the phenotype that we're looking to modulate. So what we are trying to answer is, if we perturb this particular gene in a human, what effect would it have on the phenotype, the disease trait that we're looking to affect? So where do we find data like that? We don't get to go perturb genes in humans. That's not possible, and it's not moral. So what we need to do is to rely on other sources of data. So one such source of data is genomic data, genetics. Each of us is an experiment of nature, where nature has perturbed every single one of our genes, and we can measure what the effect on a phenotype is. So good news is that genetic data is actually in a Moore's law scale. So again, the y-axis here is a logarithmic scale. X-axis is time, the number of human genomes sequenced since the first human genome in 2001. And you can see that not only is this growing exponentially, it's growing twice as fast as Moore's law. So if this trend continues, by 2025, we will have the human genomes of 2 billion people. That's a lot of data. And genotypes, of course, is not enough. You also need phenotypes or traits. Here, progress has been slower, but one of my favorite data sets is the UK Biobank, where it's actually measured for 500,000 people, multiple traits that range from blood biomarkers, urine biomarkers, physical tests, cognitive tests, whole body imaging. So a reasonable amount of data, but for only 500,000 people. You put those together and you get a mapping that allows you to go from genotype to phenotype, so that looks good. And sure enough, over the last 10 years, since people have started to look at this, there have been thousands of what's called genetic associations discovered between genes and phenotypes for traits that range from cholesterol levels to Alzheimer's disease to educational attainment. So that's great, and you would think that, great, we're done. The problem is that for any single complex traits, not the Mendelian ones that have a single gene that causes them, there's a lot of small variants that come together to give a big effect, but none of them a priori are the ones that you know are really driving the disease. So how do we go after these without spending hundreds of millions of dollars on something that might not work? So here, what we're going to do is we're going to bring in another type of data that we can produce at even larger scale than we can humans. And that's riding a revolution that's happened in parallel to what we see in computing, which is allowing us to generate disease-relevant data at an unprecedented scale on cellular systems that are relevant to human biology. A few years ago, to do an experiment at the genetic level, at the cellular level, we had to take cancer cells whose relevance to human biology is tenuous at best. Today, we can take a skin sample from any one of you and reprogramming it to stem cell status and use it to generate neurons or hepatocytes or cardiomyocytes that are capturing the individual genetics of the person from whom we got them. We can perturb those using the technology called CRISPR to modify actively a particular gene to see what effect that would have on the phenotype of those cells. And we're able to measure those phenotypes by looking at cells under a microscope and looking at individual molecules and where they are positioned in the cell and what effect does a disease gene have on that important phenotype. So we can put that together with the genetic data to see how perturbing genetics affect cellular phenotypes and how that aligns with human clinical phenotypes. So, of course, that gives us data that looks like this. People are not used to looking at data that looks like this. This is not bears sitting on top of rocks. And so how do we use machine learning to interpret that kind of high-content data without requiring the kind of prior knowledge that we used to have? And that's where I think the magic of machine learning can come in. And so so let me give you just one example of this. This is a really amazing example. This is a deletion of a region on chromosome 16. And that region is actually deleted in some people and duplicated in some people. And most people, you have just the one copy. And it turns out that if you have a deletion, you have an overly large number of synapses, and it leads largely to autism. And if it's duplicated, you have a depletion of synapses, and it leads to schizophrenia. And you can see that in these examples over here in stem cells that are differentiated from autistic patients and from schizophrenia patients. So it's a pretty remarkable thing if you could really use this now to get this type of understanding of the causal mechanisms of disease, and then use that as a screening platform to modulate those phenotypes to see what can revert this synaptic deformation to something that's more of a normal trait. So in order to do that, you really need huge amounts of cellular data. And so what we're actually building is an automation-based biodata factory that creates huge numbers of cells with varying genetic backgrounds, perturbs them, measures these cellular phenotypes, and uses machine learning to interpret the results. And that amazing feedback loop between experimentation and machine learning is what we rely on. So I'm out of time, so I'm going to end this with a slightly philosophical note, which thinks about the epochs of science and comes back to the beginning of my talk. In every period of history, there's been a science that has moved very quickly during a short period of time, due to some new insight that's come about or new technology. In the late 1800s, it was chemistry with a periodic table and understanding the connection that we cannot turn lead into gold. In the 1900s, it was physics, understanding the connection between matter and energy in space and time. 1950s, digital computing, where computers were able to do tasks that up until then only people had been able to do. And then, in the 2000s, there was an interesting bifurcation. On the one side, we have the discipline of data, which is related to computing, but is different because it also involves elements of statistics, for instance. And then in parallel, there was the era of quantified computing with genome sequencing and super-resolution microscopy and measuring transcriptional profiles. And those two proceeded in parallel without really much communication between them. Today, I think we're at the cusp of the beginning of a new age, which is the age of what you might call biodata engineering, although I hope someone comes up with a better name. And that's the era where you can measure biology in very great detail at a whole new level and unprecedented scale, bring that back into machine learning to interpret what we see, and then circle back and engineer biology to do things that it was never meant to do. And I think that will have a transformative impact not only on human health, but also on the environment, on agriculture, and on many other areas. Thank you very much.